Swayam Prabha. Digital India. Educated India.
Now, recurrent neural networks are actually the same network repeating itself over time. And over time means that as each token is seen, the machine enters a different state. The three controlling parameters are U, the uh, the weight values going from the input to the neural network. So this is not a single neuron, by the way. This can be an assembly of many neurons or a single neuron. And then from the neuron going to the output layer, another set of weights called V, and a self-feeding set of weights, which is the feedback connection. Okay. In the feed-forward network, there is no feedback, and therefore the network progresses from the input to the output without really iterating, without really self-iterating. Okay, the only iteration feed-forward network does is on the epoch of examples, input-output examples. So that iteration is externally triggered and externally controlled, while the feedback connection in the neural network forces it to self-iterate without any external signal or trigger. Okay, so this feedback connection is causing that recurrent behavior of the neural network. So the three weights U, V, and W are the parameters which are learned from the data. So this is called unfolding the left hand side to right hand side. The same set of weights feeds into the next state in every time step. This is a trained network and it is operating on a set of a sequence of tokens. So xt minus 1, xt plus 1 is a snapshot of the input, and the outputs are ot minus 1, ot plus 1, and the states are st minus 1, st, and st plus 1. So this is a state machine which unfolds over time, and time meaning looking at the sequence token by token. So example of this would be part of speech tagging, where the machine sees purchased and produces VVD, past tense verb. Sees Videocon produces NNP, proper noun. Sees machine produces NN, normal noun. So the reason why NNP is produced is because of the input, the state of the machine in the previous time step, and the three controlling parameters of weight values U, W, and V. So this is a sequence to sequence transformation which is happening. Now here is an important interesting point which can be noted. And Jyotsna, this slide has to be added because it is coming as a kind of afterthought to me. So if this was a speech to speech machine translation. So purchased Videocon machine. Videocon machine kharida. Okay, Videocon machine kharida. Now see what is happening. Purchased was in the beginning of the sentence. So Jyotsna, please note these points because it relates to things we covered, should be in the slide. So purchased Videocon machine. The purchased Videocon machine is the verb phrase. The verb coming in the beginning of the phrase. So English is head initial, right? English is head initial except for adjectives coming before the nouns. But Hindi, Bengali, Marathi, and many other languages would be head final. So Kharida will have to come after Videocon machine. Now this phenomenon is called latency. This phenomenon is called latency. Latency means that if I'm doing speech-to-speech machine translation, purchased Videocon machine will have to become Videocon machine Kharida. So you cannot produce the translation of purchased immediately, okay, after seeing purchased in the input string. So if you are not able to produce it immediately, you'll have to hold it back. And after you have seen a certain amount of text, Videocon machine, then only, uske baad hi, you can produce Kharida. So this is called latency and is an important concern or a challenge to be solved when we go from one language to another for its translation. This can also happen in what is called online machine translation. Online machine translation or interactive machine translation. So the machine, the automatic translator cannot really produce token by token translation. Okay, if the order of the words, if the syntax of the target language is different from the syntax of the source language. So if you're doing interactive machine translation, the output from the automatic translator will have to wait to produce the translation for purchase. Okay, so Videocon machine Kharida. Kharida will have to wait until Videocon machine has been seen before. Okay, so part of speech tagging is a relatively easier problem because it demands token to token action. Okay, and there is one-to-one correspondence between the input and the output. There is no switching of tokens. There is no deletion of tokens. There is no insertion of tokens. It is a straightforward position to position, entity to entity mapping. So there is no latency in part-of-speech tagging. If the two languages for which translation is to be organized, if they are close to each other, then same um, uh, convenience will prevail. So if the translation was French, then since French is also head initial and closely mirrors English, the translation also can work like part of speech tagging. So purchased Videocon machine will be French equivalent of purchased Videocon machine. I don't know the French equivalent of purchased, but let's check on Google Translate. So let's say English to French. So purchased. Okay, see that French, English, the Google translation system is an interactive or online machine translation system. Okay, it is suggesting French translations and has a bit of a disadvantage because purchased in English is gender agnostic. Same form for both English for both masculine and feminine gender. The French translation has feminine form and masculine form. Let's hear the pronunciation also. Ashte. The same pronunciation, but the spelling is different. So purchased video is a proper noun. Videocon machine. Shaste une machine Videocon. So French puts the adjective after the noun. So that transformation has happened, but it is so fast that you could not spot the latency for videocon machine. Okay. Now this is okay as far as English French is concerned, low latency for going from English to French. But if it was Hindi, videocon machine kharidi, but let me put the sentence again. I go token by token, purchased, kharida, videocon machine. So you see, it did a transformation between purchased and videocon. First, it made videocon kharida, and then when machine came, videocon machine kharidi. So this was an interactive machine translation situation. If the sentence was very long, okay, then there will be a latency period, but Google most probably puts in huge computing power, lot of machinery for the translation service. So users don't feel that there is latency. Okay, so so this is known as latency, where you'll have to wait for a piece of text to be transformed before the transformation of the current piece of text can go into the output. Okay, so let me try to give a long sentence. John, who lives in Jodhpur, which is a big city in Rajasthan, which is a great tourist attraction. So you see, it keeps on attempting to translate part by part, okay, and produces something at a point of time which may not be the right translation. Now let's see what it has produced so far. जॉन जो जोधपुर में रहता है, जो राजस्थान का एक बड़ा शहर है, जो एक महान पर्यटक आकर्षण है. So far so good, okay. But if we could do it in slow motion, maybe 1/5 the speed, then we will observe latency also. We come to another high latency situation where the decision has to come out at the end of the input. So, uh, so the first token is I, then like second token, the camera, end of sentence, and out comes the positive sentiment decision that this is a positive sentiment sentence. So this is a situation of high latency by definition because of the nature of the problem. And what the boxes show are the state transitions of the machine. The letters A are what are called attention vectors. Okay, and C is the context vector. So all these will be our concern when we discuss a sequence to sequence transforming machine. RNN is a kind of sequence to sequence transforming machine. Now, coming back to the RNN model, now I'll go a little fast application and then come back to. We have said U, V, W are the controlling parameters. Please see that we're not talking about training now. We're talking about the use of the machine in actual situation. The same UVW operates. What keeps changing is the input, the state, and the output. Now, the notation is the following. Xt is the input at time step t. For example, could be the one hot vector representation corresponding to the second word of the sentence. St is the hidden state at time step t. It is the memory of the network. And st is a function of u into xt plus w into st minus 1, where st minus 1 is the state at t minus 1, w is the and xt is the input vector at time t, maybe the word vector of the word purchased, and u is a vector which multiplies this xt. St is a function. That function is some kind of non-linearity, maybe sigmoid or ReLU or tan H function, which gives you the next state. Now we understand that all these, though diagrammatically represented as circles, arrows, etc., all these are simply different matrix operations, matrix multiplication and matrix uh, addition. So u into xt is a matrix, w into xt minus 1 is another matrix, or they could be just numbers if they are column and row vectors. Okay, so the function f operates on this quantity. So f is a function of the input and the previous state. Unlike feed-forward network, f is only a function of the input. Okay, you recall in perceptron or in backpropagation, where f is only a function of the input. You take every neuron, this is what happens. The net input arriving is operated on by f. But the additional thing in recurrent neural network is the previous state. And usually f is tan h, tan hyperbolic or ReLU, which is approximated by a soft plus. Now, tan h function is defined as e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. So this is like the sigmoid function, except that it is bounded between -1 and +1. Like sigmoid has a very simple, convenient derivative, y into y minus 1, y into 1 minus y, no, y into 1 y minus 1, whereas tan h has a little more involved derivative. Try to see what that would be. And ReLU function is defined as fx equal to max 0, comma x. So before 0, the value is 0, and there is a discontinuity at 0 with y equal to x as the behavior after 0, the gradient being 1. Now, since in uh, all kinds of gradient descent method, we cannot deal with discontinuity, we have to make a continuous approximation to this function. So that is approximated by log of 1 plus e to the power x. Okay, so this is the function which is also called soft plus function that approximates ReLU. Now, the reason why tan h is used is because we would like to make use of the full spectrum from -1 to +1. And if we multiply tan h by k, then we have the spectrum from minus k to plus k. That is important for controlling the input-output functionality depending on the problem. So in weather prediction, for example, the number of inputs is very, very large. And the sum of the inputs multiplied by the weight naturally becomes very large. So working with sigmoid many times lands the machine in saturation region. So k into 10h solves that problem by giving a large range of negative and positive values. And the reason for using ReLU is that it has been found to be it has been experimentally found that it is effective for a number of problems. Now, what those problems are, what those characteristics are, let's see if we can find time to discuss. Sigmoid, you remember, is proposed because it closely mirrors the actual function in the brain. There is a saturation behavior for very large signals, but and also sigmoid is a derivable continuous function. The derivative is a simple expression. Those are the attractions of sigmoid. So similarly, what are the attractions of tannage? We partially touched upon it. What is the attraction of ReLU? That needs some amount of discussion. Do try to see if you can find it yourself, or we'll have a discussion on this. Now, the notation continues. OT is the output at step T. For example, if we wanted to predict the next word in a sentence, it would be a vector of probabilities across our vocabulary. Okay, and OT is softmax of V into ST. So you can see from the diagram that OT is a product of V into ST. Okay, so what did I mean by a vector of probabilities across the vocabulary? So suppose I say I like to watch. I like to watch, and this is a language modeling problem. I have to give the next word. So the next word can be many things. I like to watch a, and next word movie, game, uh, mm, okay, drama, play, so many possibilities. But I like to watch a elephant. Possibly should get a low probability value because a can come before a consonant. Before elephant, I should have gotten an. Okay, so since an is not there but a, so elephant is not the likely candidate because a consonant is expected there. So there can be such semantic considerations, grammatical considerations, spelling considerations, vowel consonant considerations, all of which are uh, kind of handled together by means of probability and training. Okay, otherwise you would have had to use a rule-based system. Okay, you'll write a set of maybe 1,000 rules saying that since the next word is starting with a vowel, it is not possible after A. So you'll keep on ruling out possibilities. That is not required because you have gone through a trained model and data. So now RNN shares the same parameters UVW across all the steps. Only the input changes, and of course the state also changes. Sometimes the output at each step is not needed, for example, in sentiment analysis. But the main point is the hidden states, not hidden layer, but hidden states. So an RNN can be an assembly of neurons which are organized in the form of input, output, and hidden layers. So those are hidden layers, but and they have their own hidden state, but that is different from the hidden state that is mentioned for RNN. So that hidden state is tied with every time step. Okay, and those states are not seen. What is seen only is the output. Output also changes at every time step. So an example due to Jeffrey Hinton is instructive, where there is this recurrent neural network. This is an actual assembly of neurons. Okay, this is not really time-stepped diagram. So we have a feed-forward connection, let's say from first neuron to second neuron, W2, and second neuron to third neuron, W4. But there is also feedback connection. I mean, feed-forward reading left to right from third to second, which is W3, second to first, which is W1. So that would be a recurrent neural network because there is feedback connection. Now, when you step through time, for example, suppose this neural network is looking at entities in a sequence. So looks at the first entity, moves to the second entity, goes to the second time step. So at time t equal to 0, I have these 3 neurons. Then at time t equal to 1, I repeat these same 3 neurons. Okay, and since the connections are from first to second in terms of W2, and then second to you have W1 and W4. Okay, so these two arrows, and the third neuron fits into second neuron as W3. Okay, so see how a feed-forward network gets created through this kind of unfolding over time. Okay, so if there are four tokens, then time t1 2 3, you will get a network which is a feed forward connection. So how did the network become feed forward? Okay, how did it become feed forward? Because you are able to replicate the same set of neurons in the next time step. And how come there is no feedback connection from neuron to neuron? No, that has been absorbed by this way of unfolding. So this unfolding is a pretty clever idea, okay, which allows us to convert a recurrent neural network into a feed-forward network conceptually, and then apply all the theory that we learned for the feed-forward network. Okay, just making sure that the equality constraints hold. Okay, equality constraints hold. So now let's proceed. Okay, we'll come back to this particular machine, uh, which has its own very rich theory, which was developed by Jeffrey Hinton and Kohonen and then Grossberg. Okay, these were the non-feed-forward neural network people working at a time when neural network had become extremely low-key area. There was no funding given to neural network because Minsky, Peppard, they proved that neural networks are limited in their power. They cannot solve even the XOR problem. Okay, nobody noticed that you can have multi-layer perceptrons, and multi-layer perceptrons can have a much greater power, and they can solve nonlinear problems. So while this was going on, there was another group of people, namely Hinton in Canada, Grossberg in Boston University, and Kohonen in Finland, who kept working on neural network in its recurrent version. Okay. What happens if I give a feedback connection? So let me go into machine translation, because machine translation is a very good testing ground for recurrent neural network. If this was a course on deep learning, then machine translation will be a case study. And if the course is on natural language processing, then recurrent neural network is an instrument for the problem of machine translation. So here I mentioned my book because it gives many foundational ideas which are required in all forms, all paradigms of machine translation, starting from rule-based system going up to neural machine translation. The book doesn't cover neural machine translation. It was written in 2015, published in 2015, before neural machine translation became such a hot topic. But there is work going on. I'm working on another edition of the book, okay, where neural, of course, will have to be treated. Okay, so MT is called NLP complete with some, looseness in the terminology. And here the word complete is used in a slightly non-technical sense. NP complete problems, NP hard problems. So it is complete. The word complete is used in that sense to an extent, but not completely rigorously. All it means is that if you solve machine translation problem, you solve all of NLP problems. And NLP itself is called AI complete, which means that if you solve NLP, you solve whole of artificial intelligence problems. And AI in turn is called CS complete. That means if you solve the artificial intelligence problem, you solve whole of computer science problems. So, so machine translation, the biggest motivation is how will the world be different when the language barrier disappears? Volume of text required to be translated currently exceeds translators' capacity. So this we have experienced uh, ourselves, when there is a huge requirement for translation. One of the current concerns in front of Government of India in this situation of coronavirus and online learning is how to reach educational material to people, even in the remotest corners of the country. And those people are not really comfortable learning in English. They are most comfortable learning in their own mother tongue. So a Konkani kid sitting somewhere in a village near Goa would like to understand, let's say, uh, uh, Newton's laws of motion in his or her own language, which is delivered in English, but reaches him or her in Konkani. Okay, so machine translation has always remained right from the beginning a very live and relevant problem. In fact, the whole of computer science is said to have started with machine translation, when in 1960s USA and Russia were involved in Cold War, and each country wanted to understand what the other country is trying to do. Okay, so there used to be secret messages passed in Russian and English between the two countries, and uh, and administrators in both countries wanted to know what is getting transmitted. So Russian to English, English to Russian became a very live problem at that time. But people took a very naive view of translation. They thought that just word-to-word replacement will work. But now we know very soon it was realized that word-to-word transformation will not work because words have multiple meanings. Okay, our favorite example is bank. When bank is translated to Hindi, which meaning should I take, river bank or the financial bank? If it is river bank, then you will have to translate this as Nadi Tat, ya Samudra Tat. Okay, but if it is a financial bank, it remains as bank. So first problem is ambiguity. So it is leading you to solve the words and disambiguation problem. Then the problem of word order change. Purchased Videocon machine, Videocon machine kharida. And there is also word insertion deletion. Advised me, mujhe salah diya. Where did diya come from? So advice is salah, but advice as verb is salah dena. Okay, where did that come from? So you have insertion, deletion, change of order, okay, and then word sense disambiguation. All these have to be tackled, all of which are uh, difficult and deep NLP problems, which machine translation demands. So these issues, these challenges, and the fact that they exist is elaborated in the book that I pointed to you. Now, since there is huge demand for machine translation, automation is required. You really cannot cope with the scale. Okay, so translation industry is extremely big, billion-dollar industry, and translators are also very well paid, by the way, at least in the Western countries. Now, so I'm also tempted to tell you something interesting which happened long time back. So there used to be a translation expert in Bhabha Atomic Research Center, BARC in Bombay, and she used to interact with us for use of technology, and we would very much like to interact with her to get insights into how a translation expert does translation. So we came to be aware of a very interesting phenomenon called monotonicity. So Jyotsna, please put this in the slide. The phenomenon called monotonicity. Monotonicity means that you isolate all those phrases in the sentence whose translation will sort of have to be done together, okay, and which will move in a group. This is also called the word grouping problem. Okay, uh, I saw immediately. I saw immediately the blue sky. Now I saw immediately the blue sky. The blue sky is together. Saw immediately is together. So a chunking is happening, you see. So now मैंने तुरंत देखा, saw immediately the blue sky, आसमान. So translators do this chunking in their mind. Okay, so they divide the sentence into these chunks and then translate them inside the chunks. There is a local translation going on. And then these groups, translated groups, are moved around to obey the syntax of the language. This was a very interesting phenomenon which was revealed to us. And we also verified this by eye tracking. Very interesting. So when the translator is translating a sentence, how is the eye moving? So we find that the eye is doing a local traversal within a chunk. Okay, and then when you have achieved the translation, the chunks have been moved together. So this is one approach of one group of translators. So Josna, can you put down these thoughts? These are very interesting and important. Another group of translators, what they do is that they rearrange the sentence, keeping the target language in mind. Okay, do not translate anything. Change the order of. So how will the sentence look for I saw immediately the blue sky. मैंने नीला आसमान को तुरंत देखा. So मैंने remains at the same place from English to Hindi. नीला आसमान को comes in between. Saw immediately तुरंत देखा. So in the Hindi order you will have at the first cut, at the first iteration, the blue sky saw immediately. Okay, so the blue sky sits and comes between I and saw immediately. So this is bringing the English sentence close to the Hindi order. And after that, the monotonicity principle can apply. Monotonicity means now you can go from one group of words to another group of words without doing any regression. You don't have to come back to a place. You can go in progression from one phrase to another. So that's very interesting that there could be, two large groups of translators who first locally translate, then move the phrases around, versus translators who move the phrase around and then do local translation. Depends on your style and abilities. Now, the interesting question is, what is more convenient for automation? Okay, so put this as a thought exercise, Satyam, that suggest an alternative, a preferable alternative for a machine. Phrase movement versus local translation. Which one should be done earlier? Okay, and it will be interesting to know your thoughts, because I think it will depend on personal style and choice. So I'd request you to do the following. You look at sentences, translate them into your mother tongue, and observe what you are doing. Are you doing phrase movement first and then translation, or reverse, or neither? Actually, neither. What is your translation process? And at some point of time, we would like to do a cognitive science experiment with you, where you will sit in our eye tracking lab, and we will observe you doing the translation and see how. Okay, are you doing local translation and then phrase movement, or you're doing phrase movement, then local translation? Those are interesting research questions and very relevant for interactive machine translation, speech-to-speech machine translation, and so on. Now there is this taxonomy of MT systems, machine translation systems. Can somebody verify that you're looking at a tree, the taxonomy of MT systems?
Yes, sir, we are.
Okay. So machine translation approaches can be divided into two broad categories: knowledge-based, rule-based machine translation versus data-driven machine learning-based systems. Knowledge-based, rule-based systems They are again of two kinds, interlingua based and transfer based. That depends on how close the two languages are, the source language and the target language. The data-driven machine learning based approach is also of three kinds now. This diagram is maybe slightly old. It has example-based machine translation, which came in 1980s, statistical machine translation slightly after example-based machine translation, but mainly in the 90s and beyond 2000 actually for a long time. Then after 2010 came neural machine translation. So I'll add that branch there. So example-based, statistical and neural are all data-driven approaches, whereas interlingua and transfer-based are rule-based approaches. Our journey in natural language processing started with interlingua-based machine translation. And of course, we have gone through all different paradigms of machine translation. Though the current paradigm is neural machine translation, you cannot really afford to ignore the other paradigms of machine translation because every paradigm has taught something new for the uh, machine translation exercise. Statistical machine translation, for example, showed how alignment is so important. Example-based machine translation showed the importance of analogy and what is called translation memory. Translation memory has been a ruling idea for now 25 years. Okay. Um, uh, um, Now, when governments take large-scale machine translation projects benefiting the nation, they make available at very high cost translation memories. That means phrases which have been translated before, they are available on the interface. Transfer-based machine translation showed the importance of language distance. If the two languages are close to each other, the level at which translation should be done. Interlingua-based machine translation showed how complete disambiguation can take the language into a universal form from which, independent of any language, you can begin to generate the target language. So I go from English to this intermediate form. Now I can do a one-to-many transformation. I go from English to Hungarian, Turkish, Hindi, Bengali, doesn't matter because you have that intermediate universal form available. So that interlingua-based machine translation has now come back in a different form in the cross-lingual, multilingual embeddings, which are used by neural machine translation. So, so history should never be ignored. As somebody has said that if you ignore history, then you repeat the mistakes which were committed before. Okay, we need to have a holistic look, understanding how a field has evolved and slowly transformed itself into a very advanced state of situation. So knowledge driven and data driven. Now people do machine learning based or data driven machine translation, but a huge amount of theory has been learned through knowledge based approach. Now machine translation, why is it difficult? I'm not saying that all of us can do machine translation easily. It requires understanding of the source sentence, understanding of the target language's properties, source language, target language, both have to be understood well. Good translators know both the languages well. So they have what is called linguistic competence in at least two languages. But then you will have to also understand the situation, the semantics, the pragmatics, the lexical issues in the sentence. Okay, so is there a metaphor used? Is there sarcasm? What is the sentiment of the sentence? Is it a question or is it an answer? Is it a declarative statement or is it a exclamatory statement? Everything is required. But translators, because of their long experience and those who are innately language proficient, they come into this kind of pursuit, I would say. So machine translation is difficult because of the phenomenon of language divergence. So this is one of the main complexities of machine translation. Languages have different ways of expressing meaning. So these different ways of expressing meaning have two kinds of divergence: lexicosemantic divergence and structural divergence. So divergence means the gap between the languages. So I'm again tempted to tell you a story which is there in the machine translation NLP field very much. I'll just take 2 minutes. The story is that once human beings became interested in conquering the heaven. So they said that we'll conquer the heaven, we'll live there. So they started to build a very high tower. Okay, very high tower. It is called the Tower of Babel. So this is a mythological story. Now the gods became very afraid. If human beings come in their physical body to the heavens, what will happen to us? Where shall we go? So then they uh, uh, conversed among themselves, discussed, and gods created many different languages. So the human beings did not have any more one language, they had many languages. And the language created language barrier or communication gap. Now we know that in any large project, if there is no communication between different modules and different teams, the project is bound to fail. So by creating this language barrier, the gods prevented human beings from constructing Tower of Babel and reaching the heavens. So this is a mythological story, but it actually delivers a lesson. It says that language is the means of communication, and if that barrier is not crossed, then human beings cannot really work in harmony. There is no progress possible in life and society. So this is why we need to cross language barrier, and that is where translation finds its motivation, energy, and enterprise. And it requires automation because of the scale problem. So we wrote a paper back in 2002, which has been referred to quite extensively, and actually created a for understanding machine translation when Indian languages are involved. So this is English to Indian language language divergence, and this is focused on English Hindi language divergence. It was written back in 2002 in Journal of Machine Translation, and it is linked from my homepage also. Now languages differ in expressing thoughts. So here is an example. This is an example, a very nice example of agglutination. So this is a Finnish string language from Finnish language. I cannot pronounce it, so I'll not try. This long string, it means the English sentence, I wonder if I should sit down for a while. So much of information is packed into that one string. Now the core of this string is ist, which is sit, the verb stem. Ahta is the verb derivation morpheme, to do something for a while. So you see, ist, istahata. So if you just take this string, that means so much, to do something for a while. So sit for a while is the meaning. ISI is the conditional affix. So that indicates if. N indicates first person singular suffix. Co is question particle. HAN is a particle for things like reminder with declarative or softening with questions and imperatives. So you see the whole string means I wonder if I should sit down for a while. Now the question is coming from Han. Han is a particle for things like a reminder or a softening, okay, and conditional is EC. So this whole string, I had a Swedish friend. I have a Swedish friend. Yes, actually you have heard his name before. His name is Nivre, okay, dependency parsing, a big NLP, who gave this spanning tree based algorithm for dependency parsing, which we discussed last time, Nivre. So Nivre gave me this string. Okay, that Istahata isin kohan. I wonder if I should sit for a while. This string and English translation. Now, so much information is packed into this string that unless you do morphology segmentation, you will not be able to translate the sentence. And then these divergences are of many. Conflational divergence, for example, words conflate on translation. So the French word vomir is equivalent in English to be sick. So vomir and vomit, you can see the difference. Okay, you can see the similarity. And stab in English becomes in Hindi chure se marna. So this is called conflation. That means one word conflates into multiple words. This is another Swedish word, utrimningsplan, which means an escape plan. So one string becoming a composition of two strings. This is called conflational divergence, where in the target language the word conflicts. You have the opposite also, deflational divergence, where the multiple words become one word in the target language. This phenomenon is also called fertility. Okay, fertility. That means one word becoming multiple word. That is called fertility. Then categorical divergence is change in part of speech category. So the play is on. On is a preposition. And the Hindi is khel chal raha hai. So preposition has given rise to a verb. Chal raha hai. So that's very interesting. If the sentence was the play is on Sunday, then it would have been translated to khel ravivar ko hoga. Now on is translated to ko. Ko is a postposition. On is a preposition. That we understood before, that prepositions become postposition for head initial to head final language. The play is on, khel chal raha hai. Here you have part of speech tag divergence. So there are many more divergences, but let me take question answer now.
Sir, Kartavya asks, are there any general empty models using something like MBERT, or are there a collection of models, one for each translation pairs in services like Google Translate or Bing Translate? By general, he means a single big language model which can be used for machine translation.
Okay. So the field is moving towards that. People feel that the source language will get transformed into one universal representation. Remember the interlingua-based machine translation of 70s. And then from there, the target language sentences will be generated. So MBERT, then Muse, they give ways of representing language in one universal form. But work is happening. I do not know how long it will take to go there. And also, is it really desirable? That is another question.
Facebook very recently released their multilingual machine translation model, 100 language pairs.
Yeah. Now the other question is Google Translate internally doing that? No, Google Translate, as far as I know, converts everything to English and from English translate to the target language.
Right. Anish asks, he has a question which is not directly related to today's topic. So often user input will have spelling mistakes, but a human would be able to figure out the word, even if the result of the spelling mistake was also a valid. How do we handle this with a machine?
Very difficult. Yes. So spelling correction itself can become a very involved task. So if the spelling mistake word is a valid word of the language, then you will have to go into higher level of NLP, syntax. Does it grammatically fit there? If it fits grammatically also, then you'll have to go into semantics. Is the meaning consistent with this spelling? If meaning is also consistent, then you will have to go to the pragmatic level. That the sentence being there, is it suitable for the situation? Okay. So I gave this example of writing a formal letter to the boss for asking for leave. So there you cannot say that my mama is sick, meaning my mother is sick. So I want to leave for one day. So their mama will not fit properly. So suppose mother for some reason got misspelled as mama. So no mistake in spelling, no mistake in syntax, no mistake in semantics, but pragmatically it is wrong.
Saurav asks, what's the difference between lexicosemantic and structural divergence?
Yeah, yeah. Lexicosemantic divergence is due to uh, words and phrases. Okay, so due to stab, for example, becoming chure se marna. So these are at the level of word. The structural difference is due to order. Okay, we purchased Videocon machine becoming Videocon machine kharida. So this is called structural difference. So one is the order difference, the other is the word difference.
Kaveri asks, for hidden state in RNN, in single RNN cell, number of neurons are fixed or can we vary them?
No, no, if it is a single perceptron, which is changing state by feedback, how will you have a RNN with single perceptron? Just give it a self loop. Okay. Then there is only one single neuron, and then it will change state depending on the input. Okay, suppose one perceptron is used to do part of speech tagging. Then, or let's say the perceptron just does yes, no. Okay, by a perceptron, that means it will just decide whether the word I'm seeing is noun or not. Okay, so it is giving 1 for noun, 0 for non-noun. Then this is a recurrent neural network with single perceptron. No hidden layer neuron, but there is hidden state. Okay, fine. So we'll continue the discussions. Thank you.